All right. Well, welcome everyone to another episode of the Frontier Series podcast. My name is Nora Petrova, and I'm joined by my co-host John Burden, and we're both research engineers at Prolific. And today we're joined by Henry Conklin and Tom Hosking, who are at Cohere, and they've written this very interesting paper on compression called Learning is Forgetting, LLM Training as Lossy Compression. And so thank you both for joining us.
Thanks for having us.
And taking the time out of ICLR. So just for context, we're filming this in ICLR in Rio this year. And we've all been very busy going to the conference and attending various talks. And there's been a lot of interesting research that we're keen to hear about your impressions of the conference as well. So would you mind giving us a brief introduction of yourselves?
Of ourselves. I'm Henry, as you mentioned. Tom and I did our PhDs together at Edinburgh, working on natural language processing and how LLMs work and how we train them. And these days, I'm part-time at Cohere, and I'm a postdoctoral research fellow at Princeton. We're broadly interested in sort of understanding models, understanding what learning is, and trying to put those kinds of theoretical points in the context of large-scale LLMs that people are actually using today.
Mm-hmm.
I'm Tom. I'm a member of technical staff at Cohere. I work in the post-training team. Mostly work around model merging, but yeah, as Henry said, we did our PhDs together. My kind of background interest was in autoencoders, representations, what would now I guess be kind of old school style techniques. That interest is still there. So this, I guess there's a part of me that still cares about what's going on inside models, how they work, where they work, not just making them good.
Yeah.
Great, thanks. So as Nora was saying, your paper is called Learning is Forgetting, LLM Training as Lossy Compression. Could you give us a very brief overview of what the paper is about, what you mean by the title, what's the philosophy of learning is forgetting, right? Because that sounds kind of somewhat like a contradiction on the surface, let's say.
Yeah, absolutely. Okay, so there are a couple of things there. I think we can maybe start by saying why we did this project, right? Mm-hmm. Like the question that we sort of started from came from a level of frustration with the way that people are currently interpreting large language models. Interpretability is like a major activity now, I think, as we're all aware. There was a meta-review recently that claimed that between 2023 and present, over 18,000 papers have been published on interpretability. And you would hope that means that we have an 18,000 time better understanding of how the LLMs work. I don't necessarily know that that's the case. Mm-hmm. And so we started off thinking about an interpretability project and trying to say, what do we think is missing from the landscape currently? And I have this sort of frustration that a lot of the work looks at fractional parts of an LLM, where a lot of it tries to understand the role of an individual attention head in an individual layer, or it tries to understand what's encoded in a particular subspace in a model. And look, these models are complex distributed systems. And what we know from complexity science is that you can't really understand a complex whole in terms of its parts, that you can't reason about population level behavior by just taking one individual and extrapolating it out. And so what we wanted a way of interpreting an LLM where rather than breaking it into parts, we can give an account of the entire model with a single summary statistic over all of pre-training, rather than just individual phases or checkpoints. And so that was kind of the starting point that we went into.
So yeah, I guess what I would add as well is, I think to be clear, interpretability is really difficult. These models are crazy powerful, crazy complicated. We're pretty early on in this journey in general. One thing that I guess kind of bugs me about some of the work is, if you go looking for something, you will find it. And if you take this sort of bottom-up approach of going where is concept X stored in the model? Mm-hmm. It's trained on so much data, you will find that concept somewhere. And it doesn't necessarily tell you really very much about how that concept is stored, how it works, how it interacts with anything else. So that sort of, it has its place, but I guess for me, the interest was to take a more kind of top-down approach and say, okay, these models are learning something. They are learning a way of doing it. What is that? Without any of our own biases as to, we have we have hypotheses, we have kind of possible options, but really saying, you know, this is essentially a kind of system. We don't know how it works. How do we interrogate that without imposing our own expectations on it?
Yeah, absolutely. I mean, I think the point of saying if you go looking for something, you can find it is a nice one in that there's some now famous interpretability work where people look at an LLM and they identify that there is a particular feature in that model that fires when it is talking about the Golden Gate Bridge. And that if you intervene on it, it will talk compulsively about the Golden Gate Bridge. And when that's talked about, it's sort of extrapolated out that that means that the model has some notion of semantics. It has meaning about the world because we have these concepts that are in the world. But if you talk to someone who is a neuroscientist or thinks about semantics, semantics aren't a single point, a single concept. It's a coherent set of relations between concepts. And so this goes back to the idea that we can't necessarily understand whether or not a model has this coherent set of relations by looking at one part or one feature or one attention head, going like searching for a particular needle in this giant haystack. So that's like where we started from. That is not engaging with what the title of the paper is or what compression is about. I think for that, it was like, what we wanted to think about is what learning is in the general case and what it means to learn a solution that can generalize. And so if you think about different kinds of learning or different ways of representing data, you could have a lookup table where you just have every single thing that was on the internet and you have everything that was in the training data in a table and you just can pull it out. And that will actually be incredibly powerful, assuming that you never see anything that you have not seen before. But if you want to be able to generalize, you need to begin compressing over those individual examples and having these reusable abstractions. Rather than, for example, memorizing individual pages about the Golden Gate Bridge, having an abstraction over them which represents this concept as it exists in all of the different contexts where it happens. And so that's where we started thinking about learning as compression. This is a thing people have thought about extensively for many decades. But what we're saying when we're talking about learning as forgetting is we're saying, on some level, you need to forget the individual documents. You need to forget the individual data points that you see during training. Not what is contained in them, not the semantics that they encode, but you want to learn an abstraction over that rather than losslessly encoding each individual thing that you see during training. So when we say learning is forgetting, it's forgetting the individual items in favor of these more abstract concepts that let you generalize to things that you never encountered before.
Yeah, really good context setting. Thank you for that. So a question I was wondering about is, do you have a good intuition on whether that's happening across the model sizes, whether models are kind of following the same trajectory of kind of memorizing first and then sort of abstracting over the data? And that's why you observe the patterns that you observe when you study the models and you plot how to compress information. Is that what you say is happening?
Yes, I think is what we go for. Yeah.
Yeah, I mean, I guess maybe it's worth kind of doing a little high-level overview of how we actually do this. Because it's one thing to kind of sit here and say, oh, let's take a top-down approach and work out what patterns are going on. Doing it is hard. Do you want to...
Yeah, I mean, we use a particular sort of framework that people have talked about in machine learning for a while. There's something called the information bottleneck theory of deep learning, which came onto the scene about 2015. It's some nice theoretical work from Tishby and Slavsky, which essentially talks about how the trajectory of training can be thought of as this kind of compression of the training data. And in this context, the sort of mathematical formalism that they use not only allows you to talk about compression, but it gives you a bound where you can say something is as optimally compressed as it's possible to be with respect to the data that the model saw. And this is like a very clean idea and a really good way of giving an accounting of learning in the general case. The trick is that that paper, lovely as it is 4 pages long and is entirely theoretical with no empirical results. And people have looked at it since there's beautiful work from 2017 that applies this to a feed-forward network on MNIST doing digit classification, which confirms these predictions and does it in a really sort of beautiful way. But again, we found ourselves looking at, say, a 32 billion parameter large language model and going, is it fair in 2026 for us to take intuitions from a model on MNIST and extrapolate it out and say, yeah, this is what models are doing regardless of size? And so the way that we talk about compression is in this kind of information bottleneck formalism, where we're trying to understand what a model preserves about its inputs, what it preserves about the training data, in order to achieve the task, in order to predict the thing that it's being asked to predict. And so that's broadly sort of the way that we assess it.
I guess I love MNIST. I miss MNIST. But it's very intuitive for MNIST to say, okay, what is nineness? I guess like that seems like a there's sixness, there's nineness, there's fiveness. That's what the model is learning, right? It's learning to take the input data and extract the patterns in that data that kind of denote which data it is, which is then useful for the downstream prediction. I think it's less clear, it's less tidy what that might look like in a large language model. So to kind of extrapolate naively is very difficult.
Yeah, absolutely. Like we have strong intuitions at a small scale when the thing you need to compress is like pixel values in like a 768 pixel image. When the compression problem becomes really complicated, it becomes harder to think about what that would be, right? And so traditional examples of lossy compressors are things like MP3s, right? Mm-hmm. Where you have an MP3 and raw audio files are gigantic, and an MP3 saves space by preserving only the data you need for a goal. And in that instance, the goal is that it needs to sound nice to like us. And humans have a finite range of hearing. And so what an MP3 does is it throws away information about frequencies that a human is not going to notice. And that winds up saving a lot of space. You have the same kind of thing with JPEGs, where raw image data is huge. Humans can't detect really subtle color variations. You throw them away and you save space. And then you try and extrapolate that out, where you say, okay, an LLM's raw data is the entire internet and every book written that we've digitized, all of the text that we can find. And its goal is to generate answers that we like, or answers that are correct. And so it becomes this thing of going, okay, you don't need to retain the entire lookup table of the internet in order to do that. What do you compress over, or how do you compress in a meaningful way to achieve that goal?
Yeah, I guess I think to me the kind of goal is some sense of like a desirable output is something that comes more from post training, right? The goal is more like a kind of plausible output, I guess. It doesn't necessarily matter if the prompt is some request for information or it's some kind of partial bit of information, then the continuation should be any plausible grammatical kind of continuation of that information that would be viewed as valid. It doesn't necessarily have to be the same one that was originally seen in the training data. Maybe it doesn't even exist in the training data. But I feel like this is the sort of perceived plausibleness is the thing that is being optimized for.
Yeah, absolutely. But I guess this is going back to the question that you actually asked. Do we think that this is happening in all of the models, regardless of size? I think the answer is yes. And I think we can give you empirics that show that that is what happens at a variety of different model sizes. But there's this sort of larger point that I think comes from the cognitive sciences, which is that learning in the general case is this kind of compression. If you think about the way that you learn things in your own life, like let's say that someone teaches you how to make an omelet, right? And they're standing there and they take a red bowl and they crack eggs into it and they whisk them with a fork and they put them in a pan and they make you an omelet. If what you do is you just remember that exact sequence and you say that is what it is to make an omelet. When I use a blue bowl instead of a red bowl, you go, that's not an omelet. If I use a whisk rather than a fork, you go, that's not an omelet. And so by just retaining all of the information, you have failed to actually learn the concept, right? At the same time, if you go, okay, well, omelets are eggs in a pan, you have compressed too much of the information in order to be able to actually recover the part of this that you were supposed to learn. And so I think learning in the general case, when it goes well, is an act of compression. Yeah. And so in an LLM, granted with the footnote, an LLM that does well, an LLM that has meaningfully learned something, we expect that this would be the case kind of across the board. And we put up results across a bunch of different time series, but we have analyses of over 80 different LLMs from a variety of different manufacturers from a variety of different years. And we essentially show that they all do this same act of compression. And not only that, they converge to very similar compressions, suggesting that, like, I don't know, there's maybe one really good compression of the internet, and in 2026, most models are able to find it by the end of pre-training.
Yeah, really interesting. And the connections to how we learn as humans as well is a really interesting one. And we can dive into it a little bit later. But I'm curious about what your take is on how different, what the differences are, because there are a lot of parallels, but there are also a lot of differences in how we learn as humans. We need just a handful of examples. We're really good at seeing the connections between things and generalizing over the context that doesn't matter. And LLMs, I guess, arguably need a lot of different examples. They tend to overfit to details that don't matter. So they only, I guess, generalize if they've seen enough of the training data, and then they're able to kind of abstract away the details that tend to vary and are not that correlated with the task. So yeah, I'm keen to hear your thoughts about kind of how you reconcile the differences, but also I'm curious about if we understand the compression as kind of a type of generalization of the data. How come the models seem to have memorized passages of text and are fairly easy to elicit from the models? It seems like in some ways they're retaining quite kind of close to the reference data information, and in other ways they seem to have generalized. Is that a sparsity of data problem, or how do you think of it?
So yeah, memorization's a super tricky one, and maybe this is something we'll come on to later. In the modern LLMs are so large that the notion of what is in and out of domain is increasingly murky. I guess to answer your question, I think there's the data, the internet, kind of human language has very long tails. So the bulk of it is going to be, for want of a better word, fairly low information content, kind of normal day-to-day stuff, I guess, pretty frequently occurring. But there will be a significant portion of it that is pretty rare and pretty unique. And I think when we kind of talk about memorization, we're sort of tapping into this idea of, can we retrieve these extremely rare examples? And if the only time that a particular data point is attested in the original training data is in that context, then I guess the only way to compress it is to an extent memorize it. And this is obviously a continuum. There's going to be extremely unique kind of patterns of words or strings, and there's going to be ones that appear in all sorts of different contexts, in which case I'm trying to think of a good example, but I don't know, hello, my name is could be followed by anything. So the concept of sort of memorization in that case doesn't really make sense, because it's such a common starting point that, you know, it appears in so many different ways that you could kind of fill that in with whatever, and it would make sense. But a very specific, again, struggling to come up with an example, but a very specific comment that is phrased in a very specific way that you would not normally kind of find in a conversation is going to much more uniquely point to that.
Yeah, this is. I could give an example that is not a good LLM example. It's this interaction of what we're talking about here are frequency effects.
Yeah.
And so it turns out if you have something that happens quite a lot, it winds up being useful to have a representation that is unique to it. And so a classic example is if you think about natural language, the language on which these models are trained. In English, for example, you have past tense formation, where you can turn a verb to the past tense by adding ed, right? I am walking, I walked. But you have a bunch of irregular verbs, like, I don't know, I go, I went, where you're not actually doing a rule-based thing. You have to memorize all of the different forms. It just turns out that if you were to have a rank plot where you look at what the frequency is of a verb and whether or not it's irregular, the most frequent items are the most likely to be irregular. And so you get this interaction effect where if something happens a lot in the training data, as you're saying, then you will wind up having this sort of conjunctive or unique representation for it, even though you're overall compressing across the data. So I think that's one thing. But the other thing is that, like, I think it's important to distinguish that, like, a compression should still be able to recover the original data to a great extent. That's what makes for a good compression, right? And so if we go back to an MP3, an MP3 dramatically reduces the file size, but it still sounds like the original song, right? And so what we want is we want an abstraction over the data that is still, with enough context, able to faithfully reconstruct the data with relative precision. And so when I think about memorization, I think about it in two parts. I think about it in part what Tom is talking about, where you have these frequency effects, where you will just store things that happen often enough. But it's also the fact that if compression has gone well, you should be able to really faithfully reconstruct most of what you saw before from a much lower dimensional representation. So just because you learn a compression doesn't mean that you have entirely lost the source data on which you compressed.
No, that makes a lot of sense. There's a lot of commentary about compression meaning generalization, and it's being related to kind of AGI capabilities. So what's your what's your take on like what the connection between them is? Because as you say, you can have a very powerful compression algorithm that has no generalization capabilities. It's just very good at crunching, kind of compressing the information that's available in it. Would you say there is an inherent connection there, or is it possible to have a scheme, compression scheme that has very limited generalization capabilities?
Yeah, I mean, great question. What I would say is that like compression is not a monolith, right? And so to lay out a binary categorization of like a really big space, you can consider lossless compression versus lossy compression. And in the lossless case, you wind up essentially preserving all of the weirdness of the data that you saw. You do get it into a lower dimensional representation, but like two different recordings of the same song might share almost no bits, right? And so in that case, you have compressed, but I would be surprised if you generalized, right? Like a big sort of finding from cognitive science over the past several decades is this idea that what gives rise to generalization is similarity structure, is being able to take problems that you are encountering now and map them onto similar problems that you have encountered before. And as you sort of compress more, as your compression becomes lossy, the way that you get away with that is by collapsing over things that are sufficiently similar that you can represent them in the same way. And so I think that once you're doing a kind of lossy compression, this necessarily gives you some kind of generalization because you wind up not just needing it to look exactly like the thing that you saw during training, it can be further and further from that and still be reconcilable. Now, what we mean by generalization in 2026 with an LLM,
yeah, very tricky.
Like I'm confident saying that compression is related to generalization at this 30,000 feet level of abstraction, that this must be true. Whether or not it is like compression that gets you all of the kinds of robustness that people are looking for now is less clear. I would like to say yes, but like, I don't know. Again, it's the problem of scale. It's like we're compressing over such a complex distribution and set of data that like, you probably have to compress over some distinctions more than others, and maybe you need those distinctions later on. And so it's this real moving target where we can say compression enables generalization, but what compression over what gives you this generalization downstream is still just a really complex problem.
Yeah, I guess this is a great question. I think it's worth kind of bearing in mind that we know something about where this data has come from, which is humans in this case. And we know, or at least, well, we don't know, we can maybe quite confidently say that the way in which we produce language and the way in which we have frameworks, right? We have mental models, we have kind of
like a semantics.
Yeah, some set of rules, I guess, that there's a system that we use to kind of live our lives and have thoughts and kind of reason about the world. And the language that we produce is kind of a surfacing of that. The point being that we are not big tables of data. We do not have a kind of set of, well, maybe we do, but probably we don't have a set of kind of things we want to say. And at the time we want to say something, we kind of go and look up in the table like, oh, I have this thought. What's the, no, I don't know. Oh, it's that one. Kind of pop that up. So there's some kind of underlying system that is what we use to produce language. Exactly what that looks like, very difficult to reason about. But I think we can fairly confidently say there is some kind of underlying system. The point being that when we start talking about lossy compression, it seems to me pretty probable that a good compression, and I think this is also worth talking about, is, you know, you can compress and you can compress badly and you can compress well. A good compression of the data is going to be pretty likely to represent the original rules that we used to produce it at a very kind of high level. No guarantees, but if your compression is more complicated than the way in which the data was generated in the first place, it's probably not the best compression of that data.
Yeah.
So I think this is what it's kind of getting at, is like the models are learning a good compression. I mean, so maybe something worth saying is, although we show in the paper, models do get close to the optimal bound of compression, and they all get kind of similarly close. They're not on the bound. Mm-hmm. They're learning a good, but not actually optimal compression. So there is still some sort of, let's assume it is learning some set of rules to make this compression. Some of those rules are wrong. That's essentially what it's saying, and it does not kind of work that well, or it is overfitting to noise or specifics or individual examples that aren't that helpful. So the models are not there yet. They generalize well. They don't generalize perfectly. Will we ever get to the bound? That I don't know.
So I guess something that's maybe worth mentioning is, you know, the we ultimately the models ultimately wind up being at this bound or close to this bound.
Yeah.
Right. But the path they take through your sort of 2D space of, I think you call it complexity and expressivity, right? They take a kind of unusual path there that seems to also be vindicated in this information bottleneck theory and the predictions made by that. I guess, do you want to sort of, one, like, can you explain that in a bit more detail, what complexity and expressivity are? And I guess two, when you sort of see these paths being traced out for the first time in a way that kind of, matches the theory that hasn't been tested at this scale, like, what did that feel like, right?
Yeah, so I guess the kind of background is complexity is kind of formally the mutual information between the input and the representation. And then expressivity is the mutual information between the representation and the output. Mm-hmm. So intuitively, complexity is how much of the information in the input are we getting into the representation? And then expressivity is how well are we able to kind of rebuild the output based on the representation.
To give an intuition briefly for what mutual information means in this context, it's saying, if I know what the input to the model was, how much does that tell me about what the representations are going to look like, right? How much can I predict, knowing the input, how the model is going to, the state of the model at that time point? So that's what complexity is for us. Whereas expressivity is sort of the reverse of that, where it's like, if I know the thing that the model is trying to predict here, how much does that tell me without needing to look of what the representations inside the model are going to look like? So we're talking about the information the model sort of retains about what it is fed in, and the information that it has about its goal, or the thing that it's going to be asked to predict.
Yeah. So when the actual details of how we go about calculating this are pretty fiddly, and was I think a substantial amount of the work in this paper. But when you go and do this and you run it on a bunch of modern LLMs, the really striking thing is, and so you take the complexity, you take the expressivity, you plot them in a kind of 2D plane. The thing that really stands out is we see these sort of two phases of training. So the first phase, we see both complexity and expressivity increase. So this kind of makes sense. The model is learning to solve the task. It is learning to take information from the input, put it into the representation. It's learning to take information from the representation and reconstruct the output. This is kind of, I guess, pretty expected. The cool part is we then see a very noticeable sort of second phase of training, where actually both of these quantities decrease somewhat. So the model starts, so this is to an extent where the learning is forgetting kind of title comes from. We see very unintuitively, I think, the model starts throwing away information. and it throws away more information from the input, and the mutual information, so the expressivity sort of it decreases a little bit, but it kind of broadly flatlines. So I think the intuition for this is first the model is learning to solve the task, and it goes, look, I have this objective, I'm trying to optimize for this objective, I'm just going to find a way of doing it. I don't care what the solution is, I'm just going to try and get information in and then kind of pop it back out at the end. And then I view the second phase as kind of organizing that information and saying, okay, now that it's in there, it's not very efficient, it's kind of messy. How can I arrange that information such that the useful bits are kept and the not useful bits are thrown away?
Yeah, I mean, this is like I think that the two-phase pattern that we see there is not surprising. A, for these theoretical reasons where people had expected that to be the case, but also when we think about sort of learning in general, like if we go back to the omelet example, you do want to arrive at this compressed representation that extracts only the parts of the process you were shown that are relevant to making an omelet. But at first, when you see it, you remember the whole thing. And so you have the whole event, you have all of the data, and then as you learn, you compress over that raw experience and you consolidate it. And so unless you have that initial expansion phase where you get information in, you have nothing to compress over. And so sort of phase one is learning the data, and phase two is learning what is important about that data for the things that you're being asked to do.
I guess to kind of run with the analogy, it's like the first time you see an omelet being made, you remember the color of the bowl, you remember what utensil was used.
Yeah.
The next time you see it, you go, it's a different bowl. Maybe that doesn't matter.
Yeah.
I will no longer remember what color bowl was used. And the more omelets you see being made, this is really taking this too far. The more omelets you see being made, you'd start to extract what is relevant for making an omelet and what is just kind of irrelevant detail, I guess.
Yeah.
Like specifics. Irrelevant is a strong word.
Yeah, but if you're asking in part how we felt when we got that result, like, oh my God, that was like, for reference, that plot, each dot is a training checkpoint from a 7 billion parameter large language model, which is large. Yes. On that plot, there are 400 dots from each pre-training checkpoint. For each of those, in order to get the entropy estimate, we fed, I think it was 40,000 web pages in that we estimated the complexity and expressivity of. And so you're taking like hundreds of 7 billion parameter checkpoints, you're feeding in enormous reams of data, and then you are boiling that down to two numbers, complexity, expressivity. And all of that rendering goes to a plot, and it was, like beforehand, we were going, hopefully we get something that we could maybe say looks like a 7. And hopefully it will have this sort of trajectory. And it is like a very clean line that expands and then compresses towards the bound. And so, yeah, I think I texted Tom and Serfi at that point, just like a screenshot of the plot. And I was like, oh my God, we have a 7. Oh my God.
Yeah, it was very nice.
Yeah,
picking up the original paper again and going, oh, nice.
Yeah.
This has worked.
Yeah.
And then I guess you see it sort of apply across multiple other models as well, right? And
yeah, so this is the interesting thing where it's like, so in the appendix of the paper, we have a lot of other plots. There's an enormous number of plots, but we apply it to a bunch of different models. And part of this is covered in the main paper, where we look at, like, for the OLMO2 models, which are nice in that they are sort of open weights across training, so you have pre-training checkpoints rather than just the final model. We look in that case at a 1 billion parameter model, a 7 billion parameter model, and a 32 billion parameter model. And what we see is that the 7 and 32 have this just very clean compressive pattern, where late in training, they sort of continue to approach the bound. Even as they get close, they're sort of like eking out a little bit more compression. Whereas the 1 billion parameter model winds up late in training just sort of like doubling back on itself and vacillating away from sort of a more compressed representation. And, you know, if you think about the fact that in that model, I think for the OLMO2 1 billion parameter model, that is trained on 4 trillion tokens. It just seems like you can't crowbar that much information into that many parameters, which is something that I think people training foundation models have known for a while. Like below sort of 7 billion parameters, there is this sort of drop off in performance. And I think that we were able to sort of frame that in terms of, well, for the data complexity that you're trying to represent, you just don't have enough information space in the model in order to be able to successfully do that. But in the appendix, we have like plots for a bunch of different models. Like we have a plot for a model that I think is 100 million parameters and was trained on 14 trillion tokens. And that, funnily enough, does not give you a nice clean 7 compression pattern. It sort of vacillates around. And so this is where I think the sort of nuance to the argument is saying this clean, expand, and compress thing happens when learning goes well. When you have been able to sort of get your data complexity and your model complexity well aligned, and you have done a really good job of your hyperparameter tuning and everything else. It's not a guarantee that this is what happens anytime you spin up an LLM. It's more of a sort of ability to identify what it looks like when learning has done what it's supposed to.
Mm-hmm. Yeah. And so you mentioned these, it's about the 7 billion parameter sort of level that you start seeing LLMs that are sort of useful. Is this because which way does the causal arrow go here, right? Is it because they're useful and therefore they are they useful because you get this nice 7 and you get sort of close to the optimal bound? Or is this kind of a side effect of being able to, I don't know, you wind up getting this nice bound because you have models that are able to actually do things usefully? Like which one is maybe causing the other, or is there a confound? Like, what do you?
So, I mean, I think my read on this is, firstly, I think this is a super interesting result. I think it's always nice when your results align with kind of things that are known anecdotally, and I think it's broadly known in the community that there's some inflection point with, at least with current training methods and architectures, around 7B models start to get kind of genuinely powerful. So seeing that reflected, firstly, we're like, great, we're doing something that sort of makes sense. I think it potentially says something really interesting about language. I've had a lot of discussions, kind of, mostly very sort of high level over kind of coffee or drinks. Kind of, is it possible to separate out, let's say, the structure of language? Like the syntax, but sort of slightly more vague than that, I guess, and knowledge, like how intertwined are these things, and kind of depending on who I'm talking to and the time of the week, I kind of go back and forth on, is it possible to have a model that only knows the structure of, how language works, but doesn't really know any information? And I think that the very weak conclusion that I can come to over these conversations is, no, you can't really separate them. You can sort of separate them a bit, but you don't have to know who the president of the US is, but you probably do have to know what an object is, or what some kind of very basic world knowledge. And somewhere in between those is sort of the right amount of understanding. So my interpretation, at least, of this kind of 1B result is somewhere in between 1B and 7B. The model complexity or kind of power, I guess, becomes sufficient to learn a useful model of the underlying data, and that tells us something about that data. Exactly kind of where that point is and what the structures look like is a bit fiddlier, but I think it's really interesting that it kind of identifies this, for want of a better word, phase change, where language at its core is too complex, I guess, to be really well modeled by a 1B model, whereas at 7B something has changed, there's enough capacity, and we can learn something that works.
Yeah. And I think the question of like causal direction here is a good one. I mean, I think that it is maybe true that it is this sort of scaling laws effect that we're talking about here, where we're saying for a certain data complexity, you need a certain model complexity. And that's why we see this pattern happening. It could also just be that like the training dynamics for larger models are maybe more stable. It could just be that they are able to sort of more smoothly move through the sort of loss surface. And so we can't necessarily say why these larger models do better. We have sort of hunches largely in those two categories of what's going on. But if I think that it's this closeness to the bound that drives that sort of big performance shift between the 1B and 7B, I think in part, yes, where we have results in the paper where we try and relate these representational structures to downstream performance. And we look at a bunch of different benchmarks, and we're able to show that how optimally compressed you are with respect to C4, which is a broad crawl of the internet, which is why we sort of say that it's sort of how optimally compressed the internet is in the model. This winds up predicting a variety of downstream benchmark performances. What's kind of interesting is that it doesn't actually predict all of them. And so what having an optimal compression of the internet seems to predict are things like MMLU Pro performance, or like sort of question answering performance, where you need to have rich semantic knowledge. You kind of need to know facts about the world. And so having this compression of all of this data that has that information winds up allowing you to answer those questions. The trick is that when we look at other evaluations, like we have an instruction following evaluation in the paper, where you're being asked a question, but you're being asked it in a really specific way. It's answer this question in only 100 words and use no commas. And it turns out that being optimally compressed on the internet does not make you good at following these specific instructions about comma usage downstream, right? And so at that point, we were trying to go like, okay, so we can think of this optimal compression of the internet during pre-training as giving you a semantics, giving you this kind of like world knowledge and the relation between things as you compress and you move similar things close together. But what is post-training doing, or what happens when a model is really good at following these kinds of instructions? And to do that, we compute another mutual information where we look at preference data. And so this is part of how people tend to optimize models during post-training, is you have a prompt, like a question, and then you have two possible answers, one of which human raters or a reward model have said, hey, this answer is better than this one. And so what we do is we feed that into the model, and then we condition on the distribution that is sort of this binary distribution of, is it a good answer or a bad answer? And what that allows us to do is say how much of the model's representation space is dedicated to information about whether an answer is good or not. And that quantity, whether or not the model is representing good and bad answers differently, predicts things like this instruction following evaluation. And so that is what we think of as sort of driving some of these, like, I don't know, more fine-grained evaluations that people are interested in with LLMs. We can show in the appendix that this increases during post-training, which is kind of intuitive, that when you optimize with pref data, you wind up having more preference information. But what's really interesting to me, at least, is when we look at the pre-training results, looking at compression of the internet, larger models almost always do better. Like, it seems like having a bigger model means you can crowbar more of those trillions of tokens in. But when we look at preference information, it's like some smaller models can sort of punch above their weight in terms of how much preference information they have. And so you can have a smaller model which may have a suboptimal compression or representation of the enormous original pre-training data, but it has a lot of information about what makes for a good answer. And we think that this accounts for some of the asymmetries that we see in terms of model size and performance, where a larger model isn't always going to be better than a smaller one on these downstream tasks. And we think part of that is that you can just have a lot of knowledge about what makes an answer good, even if you don't have a perfect representation of the world or the semantics within it.
I think something else that kind of worth touching on is it's worth coming back to exactly how these models are trained. And they do not see, it's not a kind of one pass process, right? It's kind of curiously easy to forget, but we sort of look at it and go, pre-training. But the model does not get to see all the data in one go. It does not, you don't kind of have a giant batch size where you go, look at everything, figure out the rules, try again. It's a stochastic process. You kind of select parts of the data, you feed it in kind of mini batches. You do this again and again, and those mini batches are going to be biased in some way. They're just going to be through random sampling. They're going to, they're not going to be kind of uniformly distributed in terms of topic or style or information content or whatever it is. So at each step in training, the model is seeing different information, and information that potentially, I guess, conflicts with the current compression that it has learned. And so the kind of actual detail of kind of step-by-step learning objective is kind of contradictory for the model, I guess, and is quite a challenging thing for it to learn. So it's sort of, without wanting to anthropomorphize the model, but it's trying to find a route through this problem, and is getting presented with very kind of conflicting information. It says, okay, my current compression is this, and then it sees another batch and goes, but that doesn't fit. I have to kind of, and I think one intuition is maybe that each of those steps kind of, you try and put something in and it kicks something out, and then it turns out a few steps later that was actually quite useful, and it needs to sort of put it back in, and there's this constant kind of juggling act of trying to find the right balance, but in a very iterative, noisy sort of way. To not say it's the wrong way of training models, but it's just kind of how it happens, I guess. So this gives rise to, if you go into the detail of some of these, some of the plots in the paper, especially with the 1B model, you see it's kind of oscillating back and forth, and it's kind of, for again, sort of changing its mind on what the best compression might be. And I think this is a kind of result of this process, that it's not a single kind of high level thing. It's piece by piece.
Yeah. So I agree, but I feel like noise is not the enemy. I think that noise is why you compress, right? This is sort of a classical way of thinking in information theory. Like if you consider, let's say, Morse code, for example. Morse code takes the entire alphabet and the things that you would want to write down, and it compresses it to a binary signal, either dot or dash. And the reason that you do that is because when you're sending something over copper wire, it's so noisy that it is much easier to make a binary classification than it is to do a 26-way classification from something that is incredibly noisy. And so I think that the noise in the optimization process and the noise in the data are part of what make you compress in a meaningful way. It's what you were saying earlier, where it's like, it's as you see more omelets that are slightly different, you wind up compressing to an abstraction over them based on the things that are invariant across the examples that you've seen. And so while I agree that like too much noise means that there is not enough signal for you to be able to learn, without noise, I think it's hard to think of why you would necessarily compress in a meaningful way.
I agree, but I think there's a difference between the noise in the data and the noise in the process. Okay. So again, we're back to the omelet example, but because of the sequential nature of training, if you see one omelet being made, then you see another one, then you see another one. You have to retain some information between those steps. If you got to see in one go all of the different omelets being made, it would be much easier to go, I do not need to care about the color of the bowl. This is the important information. So
but by the same token, if I see all of the omelets being made at once, why would I not just memorize each instance individually?
Because you don't have capacity. That's the point, right?
I don't have capacity. Interesting. Okay. Yeah. In the limit of omelets, I agree. Yeah.
To engage with the omelet example as well. So there's the way I understand it, and feel free to correct me, is that the way up to pre-training, the model is not aware of the task that it may see downstream. So it is predicting the next token, whereas in the omelet example, we have a task in mind, and that allows us to abstract much better over the data that we're exposed to. How do you think about the differences here? You obviously explore how it links to preference data, but I guess like up to pre-training, what is the process that the model uses? I don't know what the best question is, but like what allows it to compress efficiently without knowing what the task is?
Yeah, well, so it's an interesting question. I think there are two things that I would say there. I would say one, it does have a task. And so it compresses with respect to the task that it knows, and that's next sequence prediction, right? And so what's kind of interesting, this is actually in the original GPT-2 paper, this is before post-training exists. They just take a model and they pre-train it on a ton of data. And then at the end, they prompt it and they say, do sentiment classification, or do these classic NLP tasks. And it turns out that the model actually can do that. Not perfectly, but it can do it relatively well, even though that is not what it was optimized for.
Yeah.
And so there's something inherent in this sort of auto-encoding objective that is saying, get a good representation of the space, and the features necessary to do the task downstream will wind up being present in that data in a way that a good compression should be able to recover. Post-training takes that and makes it much sharper and cleaner, but the abilities have to be there at the beginning of pre-training.
Yeah, absolutely.
So that's one thing that I'd say. The other is like, actually, it's I think it was yesterday. There was a keynote at ICLR that was talking about human children and children learning and children learning to walk. And there were these results about children learning to walk and teaching robots to walk using models that either have goal-directed behavior or just have an intrinsic exploration in them, right? And it was noting that like people used to think that children maybe have a clear goal where they're going to go and they're going to pick up a toy and then they're going to go and do something with it.
Yeah.
Where when you look at the actual sort of headcam footage of what the child is doing, the child maybe moves towards the toy and then wildly looks around and is just sort of like having a good time, not necessarily engaging with a specific task. And so I think that there's something about pre-training is this early developmental stage of learning for an LLM. To make a broad generalization that I think no developmental psychologist would sign off on.
I'm going to call you out on that leak later.
But it's this idea that like early in learning, it is really noisy and it's not necessarily cleanly goal-directed.
Yeah.
If you think about reinforcement learning, you have an exploration phase before you have an exploitation phase, where you're actively trying to make the process kind of noisy and you're trying to make the predictions kind of uniform across possible states. And then it's later that you really specialize, right? And so I think early pre-training, in my mind, is this sort of learning that doesn't necessarily have these particular goal-directed behaviors. It's sort of this exploration of the space in an incredibly noisy space. And it's later when you do fine-tuning that you wind up getting these particular things to emerge, right?
Yeah.
You're not teaching the baby to make an omelet. You do that after they have learned to walk and they have explored the space, right?
Yeah, yeah, absolutely. No, it's super interesting, and the parallels are stretched to some extent. I guess for me, I would liken pre-training to sort of predicting the next frame, which, from my perspective, is quite different to what children are doing when they are not strictly goal-directed, but they have grooves of exploration. So they're attracted to some things and they have patterns of exploring them, and then they kind of attach to something else. So that's very different to kind of trying to predict kind of the next frame. But yeah, super interesting.
I mean, yeah, I guess really stretching the analogy when children do not get pre-trained.
No, absolutely.
It's very much a kind of continual.
To clarify, the abstraction that I'm reaching for is this idea that I think early learning is noisy.
Yeah,
And
absolutely.
I think that over time, the noise kind of decreases as you have increasingly sort of task-specific signals in learning.
Yeah.
And so that's the only sort of parallel that I'm trying to draw here, is this sort of like initial, maybe less goal-directed, noisier learning process.
Yeah, absolutely. And it ties into, I'm sure you're aware of the Why Greatness Cannot Be Planned, where a book by Kenneth Stanley, that demonstrates that when you're trying to optimize too narrowly on an objective, you cannot get there sometimes. So very local optimization doesn't produce this broad generalization, doesn't produce kind of curiosity-driven behavior. And a lot of the research that I'm seeing around world modeling and like curiosity-driven exploration is perhaps trying to tackle that in some way or another. Do you have any thoughts, or are you up to date with the research in that direction?
Yeah, I mean, like, it's weird for us because we started our PhDs in 2019, which is ancient history at this point. And at that point, BERT had come out. There was an LLM, but this was not a thing that was like, and at the time I remember in our first year, the sense was like, God, if we just had more very clean task-specific data, then we would be set. If we just figured out a way to get the perfect data for this semantic parsing domain and a really good prior into the model, we could make it work. And what we've essentially learned is that actually having this hugely noisy process, which is not necessarily specific to the particular domain, is critical before you actually do this sort of task-specific stuff. So I agree with what you're saying, where if you do this sort of local optimization or this task-specific optimization, you can get a good representation, but I think it doesn't necessarily generalize that robustly. And so if you think about pre-training as learning this compression over the most data that we can squeeze into a model, I think in my mind, that winds up giving you the most sort of robust or the most flexible representation because it has the ability to compress the most information we can give it. Specializing that is then really useful. Whereas if you start with tiny task-specific data, you maybe learn a brilliant compression for that data. It's just the guarantees that that will ever do anything meaningfully outside the particular distribution that you saw. It's just much less likely, you know?
Yeah, I think I would love to hear your thoughts on this. There is a curious tension between kind of scale and generalization. So on the one hand, we know that pre-training works best when you give it more and more data, and the more data you give to the system, the more likely it is to be able to identify, to kind of hark back to the earlier point, the underlying patterns and discard the let's say sampling error, just the kind of specific instance of what has been shown to the model. But there comes a point when if you kind of run with this idea and you say, okay, let's have more data, the concept of what is in and out of domain becomes very murky. And the question of generalization becomes, well, if the model has seen all human language ever written down, obviously not every possible sentence has ever been written down, but the concept of what is kind of left over is very tricky to reason about. And I guess I find it quite difficult to kind of reason between these two things. Like on the one hand, you would like the model to try to learn the underlying system. The best way to, the more data you give, the cleaner, better representative sample it is of that system. But on the other hand, at some point, if you kind of take it to an extreme, then there's no need to learn the system because you now have everything anyway. And yeah, I don't really have an answer other than to kind of throw that out of the question, I guess.
Yeah, I mean, it's interesting, right? I think that when people started using LLMs more, I think initially I thought of it as cheating, where it's like, it's saying, okay, if I want to make this model better at generalizing, let's just make it less likely that it sees something it hasn't seen before, which seems somewhat antithetical to the idea of what generalization is. But I guess over time, particularly seeing the kinds of generalization that you can get these models to do, yeah, LLMs are quite good, I think, in a shock twist. They're relatively good at quite a lot of stuff. You begin going, okay, there is some meaningful generalization here that seems to arise from the level of data. And so it's not necessarily that it's cheating or that it's trying to sort of just map things back to something it's seen before. I increasingly think about it in terms of what we mentioned a little earlier, in terms of semantics, where our understanding of sort of semantics or the way that humans represent information is that it's not about having individual conceptual points, it's about having a coherent set of relations, right? And so in order to have a coherent set of relations that are useful for general purpose downstream tasks for interacting with humans, you kind of need to know about all of the stuff in the world that you would want to talk about, right? That's kind of key to actually having a good model of the world. And so I think that I now think of this scale question, particularly as it pertains to the data, as trying to get as good a semantics or as coherent a set of relations between the things in the world as possible. And when you do that well, when you do that effectively, and when that is a good compression, when it's a clean abstraction over those semantic concepts, I think that is the thing that more than any other part of this process enables the kinds of robust generalization that we see.
I think something that in hindsight I would love to look at is, so in the paper we only look at transformers. It's the current architecture. We only look at transformers on the kind of current open weight scale because that's what's available. But you're right that what is a good compression is really the key thing here. And I guess, like I said earlier, we don't have the best compression. We have a pretty good one, but there's room to move. And I think it's also worth remembering that like model size is not fixed. If we can achieve a equivalently good compression with fewer parameters or a kind of better compression with the same model size, to me that it would imply that we are learning a better representation of the underlying structures and system that it's generating. And it's very difficult to kind of project this forward and go, okay, what does that look like? What's next? But it would be quite fun to go back and go, okay, how we used to do things with RNNs, STMs, CNNs even. How do those compare? If we kind of imagine ourselves back with those what are now very old models, and so what did we know at the time? What did that imply about the future? I guess.
So is your like intuition here that perhaps they are, RNNs are maybe less close to this optimal bound than say an equally sized. I mean, maybe you don't get RNNs as big as large language models, but against like their sort of contemporaries, are you sort of expecting them to be, the performance is clearly worse on modern types of task? Is this because they're further away? And I guess a sort of a follow-up question to that is, if you look over the past few years of LLMs, if you take, I don't know, a 10B model from today and compare it to a 10B model from a few years ago, right? Even though they are the same size, we've made all these like improvements in things like post-training across the whole like training regime. Do you think this would sort of shift things closer towards the optimal bound that we sort of see in the paper?
Yeah, I think that would be my intuition. I'd love to run the experiments and check, but
I mean, along that we have a plot that may be in the appendix. I can't remember. We didn't put all the plots in the appendix.
there were a lot of plots.
Where it's essentially having on the y-axis how close you are to the bound, and on the x-axis is model version. So going from like Gemma 1 to 2 to 3 and moving forward, and we can see that they do get more optimally compressed version on version between the first llama and llama 2 and llama 3. And so that's not doing the architectural comparison that you're mentioning, but it's essentially this intuition that part of the picture, not the whole picture, but part of why they have gotten better is that they are eking out these marginally better compressions from the source data.
Yeah. And I guess to be, there might not be significant kind of paradigm shifts in the architectures between them, but hyperparameters have got better, architectures have changed slightly, training techniques, kind of batching, all these kinds of things are material differences. And I mean, it's worth highlighting as well, all of the analysis is done on the same data set. So although the training data used for those models is different, the data we're evaluating on is the same. So those comparisons are valid, and it is, it's not that the data is, the data probably is cleaner or better, more representative of what we're trying to learn. But the analysis is done on the same data. So that's not quite the explanation for it.
Yeah. There's also, I think we have a plot also in the appendix, which is looking at a 7 billion parameter model that matches the sort of one in the core paper. The difference is that the one in the paper is from the past year, and it's trained on 4 trillion tokens. And the one in the appendix is the same number of parameters. It is still a transformer, but that was trained on the pile, which off the top of my head, I think is like 100 million tokens, or on the order of hundreds of millions of tokens.
Yeah.
And what we see is it doesn't cleanly enter the compression regime. You sort of get some getting closer to the bound, but it is still sort of expanding even late in training. And so there is something about that increase in scale relative to the model, which I think has driven having this sort of more optimal compression. But what's kind of fun is we look at like how contextual information is represented in the model, sort of how much the current token versus the previous token versus the token before that, how much each of those contribute to the model's current state. And what we show that like over 50% of the information in these models is doing local context. It's just like the nearest 4 tokens or something, which I thought of this because we were talking about LSTMs, and LSTMs forcibly have this very local context window. And part of the reason that they were difficult is that they are not particularly good at resolving long distance dependencies, where I need something 400 tokens back that's relevant to the present. And part of the reason why people think that transformers are as good as they are is that they do not have this locality constraint. They can equiprobably relate the current token to anything in this million token context window. And that you would think would maybe give rise to sort of a different kind of locality structure. But I don't know, I guess human languages minimize dependency length. across the world's languages, humans don't really like computing long distance dependencies. We would prefer that all of the words that are relevant to each other are right next to each other. So I guess it makes sense that like when you train a model on orders of magnitude of human generated data, you wind up recovering these kinds of locality constraints. And so I guess part of what's interesting in the difference between LSTMs and transformers is I think that transformers converge to this notion of locality without being constrained to do so. And LSTMs are likely more constrained in the way that they arrive at that. Yeah, I think this goes back to some questions that you were mentioning about sort of sample efficiency, where I think that transformers you can think of as a way less biased architecture, right? It can relate anything to anything. And so I think it takes much more data in order to get it to converge to this kind of locality than it would if you had built that in from the start.
Yeah, makes sense.
Yeah, I think this direction is super interesting. Like we've talked about this a bunch in the past that we know, as you say, that language is kind of locally contextual. Words in most languages kind of relate to each other when they're nearby. But we also know that to kind of articulate more interesting statements, I guess, you need to look further back in your context. So there's this sort of tension between, it's mostly local, but occasionally potentially really quite distant. So LSTMs take one approach to this and say, okay, we're going to add what would be called an inductive bias that we will encourage the model, or in some cases constrain the model to only look at local context. That gets you quite far. But then, like you say, the power of transformers is you sort of remove that constraint and say, okay, I'm going to enable the model to make very long range kind of connections.
Yeah, sorry, I realize we're talking about local dependency structure. It's maybe useful to give an example. I think it's something where, like, if you think about sentences in English, you can have a sentence that goes like, Tom went to the shop, right? Those are all nice, neat local dependencies. If instead you say, like, Tom, who, by the way, is wearing some red shorts, and I did actually meet him in Edinburgh, and he's relatively nice on a good day, and he has some opinions that from time to time I don't necessarily disagree with, went to the shop, right? You then need to resolve went to the shop with the subject of the sentence, which is really far away. And humans can do that, right? You can interpret that sentence. We would rather not, right? And so that's sort of what we mean by this local dependency structure, is that the things that you need to resolve are very close together. But like us, we need the model to prefer that while being able to do the long distance dependency as and when is required.
So this to me is the interesting thing, is we're deep in speculation territory, but RNNs, LSTMs are kind of on one side of the axis, I guess. They're kind of aggressively local. Transformers have almost gone maybe too far the other side and gone, okay, we're going to have very little constraint on how long these dependencies could be. I wonder if there's some balance between the two of having the ability to have a long range dependency, but encouraging short term ones, because that is ultimately kind of how humans work. Whether that would be beneficial, exactly what that looks like in architecture terms is tricky. Can it be trained? Blah blah blah. But I think it also kind of comes back to maybe something I was saying at the start, that like the power of, this is going to sound like a really grand statement now, I think, but
we're speculating. It's fine.
The power of deep learning is that you don't need to know what the underlying structure is. That's the point, right?
Yeah.
We learn it from data.
Yeah.
And as soon as we try to impose something about that structure on the model, we might help, we might make it worse. Yeah. I think broadly we often make it better. We'll make it kind of better by a factor of 10, but worse by a little bit. And you kind of, it's 10 steps forward, 1 step back, and we are making progress, but we're also curiously hampering the model in some ways. And I think it's very difficult to see a situation where we understand the system. It's almost recursive, right? If you understand the system deeply enough to be able to say this is the correct and complete inductive bias that is required, you don't really need deep learning anymore.
Yeah, absolutely.
So it's kind of an impossible situation to resolve.